In this lesson, we continue to explore decision tree splitting measures where we discuss the Gini Index. Gini Index, or impurity, is another popular decision tree splitting measure often used in algorithms like CART, classification and regression trees. But unlike entropy, which comes from information theory, the Gini Index measures the impurity of a dataset. So the lower the Gini Index is the better. And similar to information gain computation, computing the Gini Index consists of 3 steps. Computing the Gini Index for the dataset, then splitting the dataset on attribute A and computing the weighted Gini Index, and then finally the reduction in purity where we take the difference of the previous 2 steps. So given a dataset D, to compute the Gini for D, we are going to find the probability for each class J, square it, sum them together, and subtract the result from 1. Here's the play golf example. To compute the Gini for this dataset, we have 2 classes, yes and no, and there are 9 yeses and 5 nos. We compute the probability for each class, 9 over 14, square it. We compute the probability for the no, 5 over 14, square it. We subtract the results from 1 and end up with 0.459, which is greater than 0, so this is not very pure. In the following step, we are going to split the dataset based on attribute A, then compute the weighted Gini Index after the split. But notice in Gini Index, the splits are binary. So we are going to find the weight of the first split, then the weight of the second split, and sum them together. In this example, we split the dataset based on the temperature attribute, which takes the values of cool, mild, and hot. And because the splits needs to be binary, we take cool and mild together. There are 10 examples, and hot, there are 4 examples. Then we plug in the values to the formula, and we get 0.443. In the fine printing, we show you what is the Gini for other splits, and we find out that cool and mild with hot is the configuration that gave us the lowest Gini Index. In the final step, we compute the reduction in impurity, which is the difference between the Gini of the dataset and the weighted Gini Index for the attribute A after the split. Here we end up with 0.016, which is a small value, which suggests that this is a good split. The Gini Index can be interpreted as something called a probability of error, or PE. So PE is the expected probability of misclassification if a label is assigned randomly on a class proportions. This is the formula for computing PE. If we expand it, we actually going to end up with the Gini Index formula for the dataset. In the previous examples and discussions, we approached the Gini Index as a 2-way split. And the reason behind that, this is how the Gini Index was adapted in popular algorithms like CART. But the truth is, there is nothing that stops us from using the Gini Index in a multi-way split setup. At this point, we covered 3 attribute selection measures: information gain, gain ratio, and Gini Index. All of these measures are great, and we're going to make some blanket statements, but the truth is, it all depends on the nature of the dataset that we are working with. So information gain is biased towards multi-valued attributes. gain ratio prefers unbalanced splits, and the Gini index tends to favor equal-sized partition and purity in both partitions. From computational point of view, sometimes computing entropy can be slower because there is a log computation, but as I just said, it all depends on your dataset. More on attribute selection measures, there is one based on the chi-square test. The chi-square test evaluates independence. If a test of independence fails to separate the samples, then the null hypothesis cannot be rejected, which means the attributes remain grouped. Some approaches use linear combination of attributes instead of splitting them into just. And which attribute selection measure is best? It's always going to depend on the dataset, and it's always worth testing different methods to see what works best. In summary, we covered the Gini index and other selection measures.